Okay, a new week, a big week this week. We have our exam. Are there any questions, general questions about the exam? You know about the time. We have a review session. Does any of you go to review sessions over the weekend? Yeah, was it good? Oh, helpful, very good. I had an office hour earlier. I'll hang around after class today for an hour if you want to talk about things. For some reason, I don't have the computer, and our assistant, does the government shutdown extend all the way to here? I didn't know California was on lockdown also, but seems like it. Anyhow, we'll get ahead. So no particular questions? Yeah, well, in the absence of my PowerPoints, we'll just go along. I think I started to talk last Friday at the end about self-inductance. The point being there that we know that if you have a coil or a loop, or you could have like n turns of this, for all that matters, and if you have a magnetic flux varying through the loop, the flux magnetic with respect to time, for some reason, could be that a magnet is approaching it or leaving, or the loop could be turning in a magnetic field, for whatever reason that the flux being the field times the area, dot product, so that it's the component of B parallel to the area being indicated by its normal, the usual story. If that happens, if a flux changes, then Faraday tells us there will be an EMF, that is an electromotive force, coming out of these wires, capable of actually pushing a current and doing some work. That, of course, is the theory of the generator. Now, the idea of the self-inductance is that if you had a loop and you passed a current through it, it creates its own flux. And that its own flux, its self-flux, induces a voltage in the wire opposing the change that created it. So the wire itself produces a back voltage if you try to change the current through it. So this creates the object called an inductor. The self-inductance relates the flux through the coil produced by its own current. So this is its own flux and its own current. And then you can use the Faraday law to say, okay, my own flux is changing, and that will produce an electromotive force, and this flux is Li. So L di, my own current changing with respect to time, will produce, there's a minus sign here, that's a Lenz's contribution, that it opposes the change. So you have the fact that you have your own changing current will produce a changing magnetic opposing EMF. Now, what's sometimes tricky here is that the EMF acts sort of like a battery. So for example, if you have an inductor, I think the example given in the book is that the inductor has a current passing through it, and the current is decreasing. It's going in this direction, but it's decreasing. I think that's the example in the text. So let's analyze that because it may be a little puzzling. If the current is decreasing, it's going in this direction, but it's decreasing. Now this thing is going to try to prevent the decrease. So it's going to try to create its own cell voltage, which will so it acts like a battery to keep that current going. So the sign of that EMF that is generated across this inductor will be in that sense, such that this current going through is trying to decrease. The battery that this generates, in a sense, tries to keep the current going. On the other hand, for example, the contrary example might be if you have an inductor and you have a battery and you close the switch, that current starts to flow through the inductor. So there's an increasing current through the inductor. What will the inductor do? It'll fight you. How does it fight you? By creating something that opposes the battery. It'll create its own EMF this way, trying to push current the other way. So it'll fight you. In fact, then you can actually draw the time dependence of the action of an inductor. Let's say you try to, let's think of this circuit here, the current as a function of time, and we could also ask for the voltage on the inductor. Well, okay, the voltage on the inductor. We could put a resistor in here just to make things cozy. See what happens to that one too. Now the current is the same throughout, so that we can have a current, it'll both be the same in the L or the R, because they're in series, and any current that flows through one will flow through the other. That's a given, or it should be given. Okay, now when you first throw the switch, they say the EMF of the inductor will be this way to try to oppose the increasing current. So in fact, at first, the current is 0. And it will rise to some level value. What is that level value? Well, what is this thing after all? It's a spool of wire. So in and of itself, it has no resistance. Ideal, this is the ideal inductor, just wire rolled in a spool, but it's just wire. So it has no resistance, the ideal inductor. So its resistance is 0 of the inductor. I have another resistance here to save the day. But what it will do, it will rise up like that. So in other words, the voltage on the inductor starts out equal to the whole voltage of the battery. I don't know whether I should make that negative, but I think you see the sign. So the voltage will start out opposing the voltage of the battery, the full voltage of the battery. What shall I call it? V of the battery? It could be the EMF of the battery. So it starts out with the full EMF of the battery, and that's why no current flows at first, because it creates so much that it completely cancels this guy driving. So it starts out the voltage on the inductor, and it will fall. Why? Because the current is not changing so fast later on as it was at the beginning. At the beginning, it was nothing to jump to something. So it's a very fast change of current. The d phi dt is very big, and it produces a complete back voltage. But after a while, the current increases slower, it changes slower, and the voltage on the inductor is less. By contrast, the voltage on the resistor goes the other way. Why? Because the current is getting more. The voltage on the resistor, I knew that was going to happen. It happens with this all the time. V on the resistor is I times R. And I is going up like that, so V is going up like that. So after a long time, this thing acts like it's no longer producing any EMF, nothing, there's no drop along here, and all the current is limited only by the resistor. So you have a circuit of this, basically, and this is out. After a long time, this is just a wire, and you just have a V over I equals V over R. So I will end up being, the limiting I is V of the battery over the resistor. And at the end, the voltage on the resistor will be IR, which will be the voltage on the battery. So that's the way the thing works. That's the way self-inductance works. So I don't know if you've ever done any of your electronics. Inductors are sometimes referred to as chokes, C-H-O-K-E, because it chokes off the current. If you try to push current through it, it'll fight you back. Yes, sir?
I just wanted to ask, so why does the grid gradually increase?
Oh, well, at first, there's this big back voltage from the inductor, which stops it and chokes it off at first. But then the current doesn't want to change so fast. I go from something to nothing very fast. But once the voltage is on, it will just increase with a certain time constant. The time to go about that far is called a time constant. It's L over R, meaning that in a time, depending on how big the inductance is and how big the resistance is, you get this kind of exponential. This is more than you wanted, I'm sure. But you get something like this T over this tau growth of the thing. So at first, the change in current is very big, and you get the full back voltage. But after a while, this back voltage decreases, so the current actually slowly increases over time like that. Okay, so that's one feature of the self-inductance. The other feature that you're aware of, and I think you may have had some homework about it too already, is that the fact that you have a magnetic field here means that there's actually energy stored in the magnetic field. Now, we came to a similar idea in the case of a capacitor way back when, in your youth. We had this structure here, and we said that if you have a plate and you have an electric field between here, that there was an energy stored in the electric field. I think, if I remember rightly, something like a half epsilon naught squared, epsilon naught times E squared over 2, something like that. You could store that. The reason was that you did a certain amount of work in carrying charges from one plate to the other to create this electric field in the space. The work you do is the force times the distance, and the force is the electric field times the charge times the distance. When you go through that story, you end up that you have built into the electric field this stored energy. Again, I remark that there's going to be something like that going on, because we do get energy delivered to empty space, as we said, from the sun, which warms us, keeps us alive. So that light, which is an electromagnetic field, as we'll get to in the next chapter, the light is an electromagnetic field. It's composed of these electric and magnetic fields, and they must be delivering energy from the sun. And this is a quantitative expression of that. In the case of the magnetic field, as I said, the analogous structure to the capacitor for electric fields is the solenoid for the magnetic case, where you have a current going through here, and you have current looping around the surface. If I put the current in here, it comes around, it goes this way, up through here, say, up through here, up through here, up through here, up through here. And by right-hand rule number 1, I can say that I have a magnetic field going in here and out here. Do we agree on that? So if this is a finite loop, a solenoid, it acts sort of like a north pole here and a south pole here, right? Flux lines coming in, coming out. Around in here, the very little flux should leak out. If you get the coils close enough together, the fields will cancel out. And in an infinite solenoid, we can say that the field is confined within the inside of the solenoid. Okay? So if we do a similar thing to this, we integrate the amount of work that's done in putting current through this in order to build up the magnetic field. It will turn out that, I think by analogy, I'm just going to put, for E, I'm going to put B. Now, I don't even remember this, and I count on my notes to do it, but I'll just use my regular analogy that when there's an epsilon on top, there's a mu on the bottom, and then it has the same form. So I'm going to guess, maybe you can check in the book, but I'm going to guess that that's the form. I might have been using the epsilons upside down, frankly, but it'll be something like that, just by the luck of the draw. Okay, so that's an important feature of magnetic fields, that they actually store energy. And I can demonstrate that a little bit here by this monster inductor here. This is not your typical inductor that you find in an electronics box, radio or something, although they all have inductors in them, or you have to worry about the inductance. But this is a lotto turns, so it's a solenoid, and as you recall, the solenoid, I think, had something like this. It was mu 0 n I, where n is the number of turns per unit length here. I think we have quite a few turns per unit length, and maybe layers of turns here, so it's quite a lot. And to make things even jazzier, we have a slug of magnetizable material here. So the mu is actually multiplied by a mu r, or relative permeability, to take into account the magnetic material, which might introduce another factor of 3. So we get a very big magnetic field inside of this thing. Now, what this is doing is, let me be sure I get the circuit right. In fact, I have a diagram here someplace, I believe. Yeah, so what this is your battery, pretty low voltage battery. These are like 6 volts, and I think they are in parallel. Are they in parallel? These darn things are, let's see, red going to, I don't know, but whatever it isn't much. It's like 6 volts or 12 volts or something like that. Pretty piddling. So piddling, in fact, that this is a lamp that wants 120 volts. If I give it 6 volts or 12 volts, it's going to be pretty dim. In fact, the circuit looks something like this. We have a battery here, 6 or 12 volts, whatever it isn't much. And then we have this giant inductor, like that. And then we have the lamp over here. So that's the circuit with the switch in it. okay, something like that. Now when I throw the switch, let's analyze what the circuit is. You're going to have the 6 volts, or whatever it is, 12 maybe, 6 I think it is, in parallel with the inductor and the lamp. Okay, so it's fine, 6 volts is fine power, 120 volt lamp. It's not going to do too well, it'll be pretty dim. And then, so that's when I connect it like this. But in the meantime, it also has current. This guy's in parallel, so they're both going to get some current, right? They're both seeing 6 volts, say. Current will be flowing through here and building up the magnetic field while I'm got it connected. Then what I'm going to do is open the circuit. And so the circuit will then look like the inductor across the lamp. And so the energy that's in the, now let's see if we can guess this right. The current will be going like this through the inductor and around like that through the lamp. Now when I open the circuit, the current that was going this way, since there's no voltage here anymore, it's going to try to drop, right? So the inductor is going to build up its own voltage this way to try to prevent it from dropping. And so it's going to create like its own battery and send current up through the lamp. See that? So the inductor, and one way of saying it is the energy that was stored in the magnetic field is going to be dumped back into the lamp. So let's see if that works. I'm doing this only because this lamp is so dim when I just start it that you may not see it way back yonder. So let's see, I'm going to close it and put 6 volts across that little lamp. Ah, he's nice. Okay, but now if I open it up, you see it dumps the energy that was in here through the lamp. Do it again one more time so you'll see it. A little glow is better than none. Light a lamp and the world will be brighter. Okay, but when I let it go, I get a big voltage created by the power that was stored in the energy that was stored in the lamp, in the inductor. I like that. Is that clear how that works? I hope so. The other thing that we'll move on to now, yes? Not necessarily. It depends. Sometimes you can get a better, lower energy state by having kind of disalignment internally. And then you need you're asking a good question, which I hope to get to later, like what goes on in a ferromagnetic domains. That's what you're asking about. Didn't really enter here much, but the point is that if you look at it, sometimes you can get domains in a ferromagnet where, for example, you can get something like this: north, south, south, north, south, north. See, things like this: south, north. You see, so some kind of peculiar arrangement where the thing would rather not be. It could end up in a state like that. Then what you do when you magnetize something, which is what I tried to do. Remember, when I had a hacksaw blade, started out unmagnetized, started something like this, pretty much, in south and north, wouldn't jumble. But then when I ran the powerful magnet over it, with the hacksaw blade case, I ran the magnet over it, so I more or less pulled all these domains in line with each other as I moved it, and I created a nice, strong arrangement. So you can do that. But over time, what might happen, just with thermally, the orientations jiggle with respect to each other, and they can take somehow a lower energy form like that. So that's an interesting question. Well, I hope to get to it when I talk about different kinds of magnetic materials. But that's what goes on in what's called a soft ferromagnet. That is to say, it's soft in the sense that if you leave it alone, it's going to sort of lose its magnetism. There are those that are what's called hard ferromagnets, the very strong ones, where they have sufficiently strong internal anisotropy, which have a preferred direction. And once they're lined up, they'll stay. But then you have, like, you can think of soft iron magnets. They don't mean the iron is soft, they mean the magnetism is soft. So there are these little details. But that's a very interesting feature of ferromagnetism. Okay, now the thing that I think is very important, very interesting, very important to understand is transformers. Let me motivate this a little bit for you, because you use transformers all the time, whether you know it or not. Yeah, you use these kinds of gadgets. Does anybody have one of them with them now, today? With you? No? Okay, well, when you get home, I'm sure you have one in your house for sure, because this is how you charge your computers and stuff like that, all your electronics. Most of our electronics, my absent computer as well, you see, we plug stuff into the wall, but the computer doesn't want to see the voltage that comes out of the wall. It's 120 volts, and it's alternating. We'll explain alternating later. And the computer really wants to see like 10 volts steady. Steady because the devices inside the computer are semiconductor things, and they don't want to get hot. They don't need a lot of voltage. They don't need a lot of current. So you need a small voltage. And when you look on this, for example, this one, it says, you look on yours, anybody have it? No? Okay, it says input 120 volts, 60 hertz. That's what comes out of the wall. 120 volts, 60 cycles per second. Output 15 volts DC. DC means direct current, steady. 300 milliamps. That's this one. So, and also shows the polarity. Which one is, if it's steady, one is plus, one is minus. And it tells you whether the outside part is plus and the inside part is minus. Because that could matter too. If you have a device and you want it plus on top and minus on the bottom, you wouldn't want to put in a voltage minus on top and plus on the bottom. So you want to get the polarity right. And some of these, you can actually adjust the polarity. If you get one of those, you can adjust the output voltage. I have one like that because you never know. Sometimes they want 6 volts, sometimes they want 10, sometimes they want 5. And you can buy these where you can adjust the output voltage and the polarity.